Question number 23rd. It says three identical small discs rest on a frictionless horizontal floor. One of them is projected along the floor to successively collide elastically with the other two and thereafter to move in its original direction with half of its initial speed. Assume that the floor is marked as xy plane and initial velocity of the first disk was along the x direction in positive direction. Find velocities of the other two disks after the collision. So there are three identical disks. So let's say one disk is this, another is this, third is this. And this one is having velocity in the positive x direction, which is u. This is the initial scenario. Now this one is going to collide first with 2, then with 3. Now these are identical and collision is elastic. So if they are going to collide head on, then you'll find first will come to rest, then second will moving. Then first is not going to collide with 3. Since the question says this first one is going to collide successively with the 2. That means the collision between 1 and 2 must be oblique in nature. So then after, let's say this collides obliquely with 2, then after one will get a velocity maybe in this direction or somewhere, so that it further collides with this. And again, this first is also going to collide with third in oblique fashion, simply because after this collision, this one has a velocity along its original direction. So the collision of 1 and 2 is going to be oblique, and the collision 1 and 3 is also going to be oblique. And we know this elastic collisions and identical bodies, so along the line of impact, velocities are exchanged just after the collision. Now, since we got to know that this finally, this one ball is going to move in the original direction, this says a lot more things. This says that when the collision between 1 and 3 took place, that was oblique, and the velocity of 1 before this collision with the 3 must be along the y direction as well as along the x direction, and the line of impact between 1 and 3 must be along the y direction because 3 was at rest. So along the y direction, velocity of this 1 will become 0. Moreover, this was at rest, so it will get the velocity in the direction where the line of impact is going to be. And we know that vertical component has gone, that means y direction velocity is going to come on the third. So this 3 will have a velocity only in the y direction. It can be upside, it can be downside. I have shown it upside. And this is going to be the final velocity of 1, that's the question says itself. So we have settled that 3 is going to have a velocity in the vertical direction, that means y direction only. That means before the one collided 3, one had velocity along the x direction as well as along the y direction, which means when this collision took place between 1 and 2, that was oblique collision, and in this oblique collision you will find this 2 is going to have some velocity in this plane, maybe x component, maybe y component, and then we need to think about whether this is going to be x component alone, y component alone, or both. So we can start like the 2 is going to have both component, x component as well as y component. So let's say this is velocity of 2 in x direction, velocity of 2 in y direction. Now we know that if we consider this entire system together, so there is going to be linear momentum conservation. So we can have a linear momentum conservation in x direction. So in x direction, if we conserve the linear momentum, then we'll find initially this was the only momentum mu. Finally, this third is not going to have any momentum in the x direction. That for sure. One is going to have momentum mu by 2. And then there will be any momentum if at all this 2 has in the x direction. So we can write it as m v2x. When we simplify it from here, we got to know that velocity of 2 in x direction has to be u by 2. So in order to conserve the momentum, there has to be velocity in 2 of 2 this along the x direction, and velocity we got to know is u by 2. Moreover, we can say this entire system will have a linear momentum conservation in y direction as well, because this xy plane, right? So it's frictionless plane. In y direction, initial momentum was 0, so final momentum should be 0, and this 3 was moving along the y direction. That means 2 must also have a velocity in the y direction. And I have assumed the velocity of 2 in y direction in this manner, that means negative y direction. So it's going to be like mv3 minus mv2y. This is mv2y and v3 must be equal. v2y and v3 must be identical. So they must be equal and opposite. Now, so we got to know that this is going to be, this 2 will have a 2 component of velocity, 3 will have only 1 component, and this was given to us. Now, still we are not able to find out the velocities because we have here 2 unknown and 1 equation. This we got to know. So collisions are elastic. We can use this condition because we know in case of elastic collision, total kinetic energy gets restored. So whatever the kinetic energy was initially, that will be coming ultimately later on. So we can say initial kinetic energy must be equal to final kinetic energy. This can be said for case of elastic collision, you know that. So initially kinetic energy is going to be half mu square only for this first object, and then finally you'll find this one will have a half mu by 2 whole square, 2 will have half m vx 2x square plus v2y square. I'm writing directly, otherwise you write under root of this square and then square of it, so under root will get cancelled out. And then the third will have half m v3 square. Half m will get cancelled out, then you'll find you can simplify this, and once you are simplifying, then you'll find this u square by 4, this is u square going to come here, so that will make us 3u square by 4, so that's a 3 square u square by 4, and these terms will be adding up like v2x square, v2y square plus v3 square. So that's another equation we are getting. Now v2x is known to us, that's the u by 2, we can substitute over here. And we also know that these two numbers are identical, so we can put in terms of v3, let's say. So that will be v3 square, that will be v3 square, that is going to be u square by 4, that goes here. So that will become u square by 2. So ultimately you are going to get it as 2 v3 square is equal to u square by 2, which basically says v3 square is equal to u square by 4. Now you take the square root both sides, so v3 must be plus minus u by 2. Why plus minus? They are simply for the direction purpose. So v3 can be upside, v3 can be downside. So we will say v3 is plus minus u by 2. That means third particle's velocity is going to be, or third ball's velocity is going to be u by 2, either in plus y direction or minus y direction. So we can write v3 vector is going to be plus minus u by 2 j cap. Now what about this second case, second ball velocity? So second ball velocity will have this I component. So I component is going to be u by 2. So u by 2 plus I cap, that's for sure. Because it was given that it was moving, the first was moving plus x direction. So this must be plus x direction, and it is coming to be plus x direction. Now v2y will be equal to v3 in magnitude and opposite in the direction of this. So if we take the plus for v3, the plus j cap for v3, then this will be minus j cap. So point is, if we are taking as a plus minus, so this will be minus plus. So minus plus u by 2 j cap. So ultimately v2 came out to be as a vector u by 2 within bracket I cap minus plus j cap, and then v3 is plus minus u by 2 j cap. So these are the velocities, possible velocities after the all possible collisions, or the collisions that it has been stated over here. That's how it's done. Thank you.